Okay, in this lesson we're going to find out how to use double integrals to calculate the centre of mass of thin plates. Now, a very common problem from physics and from engineering is to calculate the centre of mass of some given shape or some given object. And one of the motivations behind that is if we know the centre of mass, then we can control the object in question. So here we've got a thin plate. So we're just working in 2 dimensions here. And it covers the region bounded by these curves here. And in particular, the plate has a density function associated with it. So rho, I've used the notation rho to signify the density function. Here A is a constant, a positive constant. We're asked to calculate the total mass of the plate. Okay, so we'll use double integrals to do that. Now, our first step with these problems is to actually sketch the region that your plate covers. Okay, so what I usually do is I draw these curves and then look at the region that is enclosed by those curves. So let's have a look. Okay, so I've got, this is like the top half of a circle. Okay, these are just straight lines. So this is my plate. So this is our region. Okay. Now, to calculate the total mass of that plate, we're going to use the following formula. So the mass is just the double integral of the density function integrated over the region omega. All right, so to do that, it's a good idea to, first of all, sketch the region. We've done that. And then mathematically describe the region through inequalities. The reason we do that is because we need to use those, that description when we set up our double integral. So this is the curve y equals root a squared minus x squared. I've got 2 vertical lines, x equals a and minus a, and 1 horizontal line, y equals minus a. Okay, so let's see if we can describe our region. All right, well, I'm going to use a vertical line here. Think of that vertical line. That vertical line enters the region at this curve here, y equals minus a, and it leaves the region at y equals root x squared minus a squared. So that would be the 2 bounds for our y. Okay, and now let's take that vertical line here and move it from side to side. What kind of interval do I need to move it between on the x-axis to sweep out the region? Well, I want to move it from minus a to positive a. So that's a description of our region. Okay, so let's use our formulae up here to calculate the total mass of our plate. So the mass of omega, let's just write that as m. is just this double integral. And what I'm going to do is actually, I can simplify things a little bit if I sort of just write this in here and leave it in this dA form. Now, if I expand this into two double integrals, you'll see that a, the little a part, gives you some sort of simple version. Now a is a constant here, so I can take it out the front. Now what is this? This is just little a times the area of omega, this one over here. So actually I don't need to do any integration there, I just calculate the area of omega and multiply it by little a. So that's pretty good. Okay. Now for this one I will have to do some calculations, so I'm going to write in the limits of integration for this first integral. Okay, so y is between this and this, so I want to put, and it's on the inside, so I want to put the dy there. Okay, so the region omega, it's just a rectangle and sort of half a disk. So it's not too hard to calculate the area, and I just want to multiply it by a. So meanwhile, while I wanted to calculate this, so I do the inside integral first. I integrate with respect to y, so I get a half y squared. Okay, so little a times the area of this, well, just the area of that half disk plus the area of that rectangle. Okay, so I've saved myself a little bit of time there just by looking at the area. Now when I sub in here and here for these limits of integration, let's see what we get. Okay, when I square that, I'm going to get something like the following. Minus a half a squared. Okay, so now it's just a single integral that I can evaluate. Now you can see if I expand this, the half a squareds will cancel out. So actually I've even got a bit more simplification to do. So I'll just be left with minus a half x squared dx plus a times this. Okay, so if I integrate this, I'm going to get something like minus 1/6 and when I sub in and clean up, I'll get this. Okay, so there I've just subbed in, I've cleaned up a bit and I've factorised. So this then would be the mass, the total mass of the plate. You can hopefully see that there was a little bit of time saving going on here and here. Okay, so that's always very powerful to try to look at area if you can. But let's look at the bigger picture. Anyone still going? Okay. If we have a thin plate or laminar and it occupies some sort of basic region in the xy plane, and we have a known density function. Then to compute the total mass of the plate, we can use this double integral here. Now in lectures, I've given some formal justification for this. Essentially it's just you start by slicing up the plate into little rectangles, and then you use the relationship between area and mass and density. Okay, remember we're only working in 2 dimensions here. If it was 3 dimensions, it would be the relationship between volume, density and mass. Okay. As I always say with double integrals, triple integrals, any kinds of integrals, it's always helpful to draw a picture to understand the geometry of the problem. Okay, if you've got to describe a region and you don't draw it, you've got less of an understanding to work with. So here's another example for you to do. Suppose we've got the same plate and the same region in the same region. Here is another density function. Go and find the total mass of that plate with that particular density function.